Okay, for those just joining, we're going to start in just a minute. I'll be hosting a review session for the final exam for our Introduction to Material Science and Engineering course. We'll get started in just a moment. Okay, while we are waiting for people to hop in, everyone to get here, you can start posting your questions in the live chat and I will answer them in the order in which I get them. Okay, we'll go ahead and get started. So for people just getting here, welcome. This is the online review for our final exam for Introduction to Material Science and Engineering course. We're going to be going through the materials that I've posted on the study guide, answering specific questions about material science content, as opposed to questions like, is such and such going to be on the exam? So I'm just going to take these in the order in which I see them come in. So the first question I see comes asking about kinetics. So specifically, since the only thing on the study guide about kinetics is either nucleation from melt and kinetics from the Avrami equation, let's just start with that. So let's come down here and talk about the Avrami equation. So the Avrami equation is something that we saw in chapter 11 on kinetics, and it was useful for describing the transformation of something, for example, crystallization of a polymer from an amorphous state to a crystalline state. So let's find the equation right here. So here's the equation that we learned about in the course. It said that y is equal to 1 minus the exponential of negative kt raised to the n, where y is going to represent the fraction that has been transformed. The Avrami equation, if it's unmodified, then it's starting from 0% transformed and it goes all the way to 100% transformed. So it's going to go from 0 to 1. And what we need to know is k and n. Those are going to be time-independent constants. They may well be temperature dependent, right? Typically transformations happen faster at higher temperatures, for example, but k and n can be determined from a system, and then we can, once we know those, we can figure out the fraction that will be transformed after any arbitrary time. So I'm going to go ahead and grab this equation. We'll bring it over to our review session. These notes, by the way, will be posted on the course canvas later. So right now, if that's our equation, how would you go about using this? To use this, you would have to be given, typically a problem like this, I would give you enough information so that you could solve for k and n, and then use k and n to determine some degree of transformation. So for example, if I gave you a table that had y and it had t, right, and you had a couple of values, like for example, maybe it said that the fraction transformed was 0.3 over here, and that happened after, say, 500 seconds. And if you measured another data point and it was 70% transformed, and that happened at, I don't know, 1500 seconds, then you could take this information and write out two equations for two unknowns, and then use that to solve for k and n. Okay. Once you know k and n, you could solve for any arbitrary transformation. For example, maybe I asked you how long would it take for it to be 99.9% transformed. And at that point, it would be as simple as saying 0.999 equals 1 minus your exponential of the k value, negative k value that you would have solved for, times t, which you're going to solve for, raised to the n, which you would have solved for. So that is how we would go about using kinetics for using the Avrami equation. Now, nucleation from melt is a broad term. You'll want to go back to chapter 11 and review the first two big parts of this chapter. I'll scroll back up to it quickly. The first two big parts first started with homogeneous nucleation, and we talked about homogeneous nucleation being if it was a sphere, for example, nucleating in the middle of a liquid and slowly growing, as opposed to heterogeneous nucleation, which is when the secondary phase growing from the melt, the solid, for example, that's forming out of the liquid melt, happens along a surface or an impurity. So you'll want to go back to review first off, why does nucleation occur? What is the barrier? We talked about surface energy, that as you form now a solid in the midst of the liquid, you now have, a surface interface between those. Interfaces are dangling bonds, and so that's going to cost us energy. Um, the ratio, however, of the volume of material that is nucleated to the surface area of that is going to be different depending on the size of the material. So in a heterogeneous one, it's going to be the cap of a sphere. In homogeneous, it's going to be an entire sphere. So there's a different ratio. Okay, so the next question was, what chapter is XRD? XRD, X-ray diffraction, was covered in chapter 3. When we learned about crystal structures, we also learned about X-ray diffraction. So if you scroll down to the end of chapter 3, that's when we started getting into X-ray diffraction. We learned about Bragg's law, destructive versus constructive interference. So back in chapter 3. Somebody asked, can we go over Weibull and a problem? Sure. Weibull was something we covered in chapter 7 at the very end. And the idea behind Weibull was this concept of probabilistic failure analysis as opposed to just using a design factor or a safety factor. So we said that in a better sense as engineers, we should learn how to model our data using some sort of equation where now we can see how well our model fits to that data. And once we have that equation, we can use that to have probabilistic performance. And there's many equations that you could choose to use to fit your data, but a convenient one that we're going to use in this class and that many others use is the Weibull modulus equation shown at the top here, where it says f is equal to 1 minus the exponential of negative sigma sub f over sigma sub 0 raised to the m. In this equation, f is equal to our failure probability. So that's going to be a number between 0 and 1. If f equals 1, then you have 100% certainty that your material is going to fail. If it's 0, then you have certainty that it will not fail. And at 50-50, right, at 0.5, then you have half of your material failing. Hence, it's the average strength. Sigma f is going to be whatever causes your material to fail. So here we've written it with sigma because sigma is the value that we use, is the character that we use for strength typically, but it doesn't have to be strength. It could be time until failure or elongation or other parameters. Most commonly, it's going to be strength. It's going to be some sort of stress that causes it to fail. Sigma naught and m are the two fittable, fitting parameters that we use to make our data fit to this equation. So sigma naught is just a scaling parameter. M is just a parameter. We give it a special name. We call it the Weibull modulus. Now, normally when you do Weibull equations, your data is going to look like some sort of distribution, right? Oftentimes maybe a Gaussian distribution. So how do we fit that to this equation? The simplest way to do that is to make this equation linear. So how do we make it linear? You can see the mathematics here when we step through it. Essentially, you're going to have to separate out your variables a little bit, and you end up on the left-hand side, this natural log of 1 over the quantity of 1 minus f. And on the other side of the equation, you've got two terms. One term is Weibull modulus times natural log of sigma f, then minus Weibull modulus times natural log of your scaling parameter. In other words, if we take this right-hand side of the equation and we have this natural log of sigma f, that will be the x value that we're going to plot it against. And if we put this entire left-hand side of the equation and make that our y, then this should be a straight line where the slope of that line would give us the Weibull modulus, and the y-intercept of that line would be equal to the negative of the modulus times the natural log of our scaling parameter. So we gave you some examples of this on a homework. You worked this out. Here's an example from the literature where they took PVA fibers and they tested them at different temperatures. And at each temperature, you can see all the different data points from actual experiments. You see that how they line up, they're mostly linear equations, right? A linear fit can be obtained. If your data can't be fit to this straight line when you transform it in this way, then you can't use the Weibull equation to simulate your data. It doesn't fit the Weibull data, so you need to find something else to fit it with. In this class, we only will do the Weibull equation. You can see in this data set, they've got, 5 different temperatures, and the slope for the first 4 is kind of constant, pretty much, right? You see the Weibull modulus is 23, 28, 28, 26. It's pretty constant. It's not changing very much. but something happens at the black triangle. At the highest temperature, at 220 C, look at that slope. It's gone way down. So something has happened to your data. There's been a transformation from one mode of failure to another, where at this highest temperature, you have a lower modulus. A lower modulus means that the distribution of failure happened over a broader range of the failure criteria. So the first four ones at low temperatures, they failed in a sort of tight bunch. Like their standard deviation, the error bars on their failure was smaller than at this highest temperature. So how do you do a typical problem like this? Well, there's lots of ways that we could ask questions about this. For example, I could provide this data. Maybe I provide a data that's already been fitted, where for this, for example, I could provide a y equals mx plus b linear fit to that data. And then I could ask a question like, okay, given that fitting, that Weibull fitting, you tell me for these test bars, what would be the stress that would cause 1,000 out of 1 million to fail? So to answer that question, your failure probability, right, F is going to be 1,000 minus 1/2 divided by 1 million samples. So basically that minus 1/2 didn't do a lot for us. It's going to be really, really small. But that will give us our value of F. Okay. Once you have your value of F, you can plug that into natural log of 1 over 1 minus F and get some sort of value here, right? That will equal some sort of number. You then would plug that into your y in this y equals mx plus b. And since you are given the value of m and b from the fitting, you can solve for x. And then all you have to remember is that x itself is equal to the natural log of the failure criteria. So to get the actual value at which it fails, you just take the exponential of x, and that will tell you some sort of stress at which this thing failed at. That's the typical type of question that you'll see with a Weibull modulus. Of course, you could go the other way. I could say, okay, for a given stress value, say 500 MPa, what fraction of our parts would you expect to fail, right? And so you would just work this in reverse at that point. You would take your stress and switch colors real quick, right? Being provided the stress, you would solve for x. Once you have x, you would plug it into the equation, y equals mx plus b, right? Then you would solve for y. Once you have y, you'd solve for f. And maybe I'd say out of 100,000 samples, how many would fail? And you would solve for the number, the rank, right? So that's the typical way that you do this with Weibull modulus. There are some exceptions or some additional things that you might see. The most common is going to be to consider, okay, what about when we test larger components, not just tiny test bars? What about when you test larger ones? So to do that, we need to know the ratio of the effective area of our components. Now, effective area, effective volume, in this class, we're treating those as the same. That's not strictly the case, but for this class, that's fine. But it's that ratio of those components that will allow you to figure out what stress your component will have the same failure rate as your test bar, which is the key thing. Like if you want to know, like for example, if we figured out that our bar has a 3 in 1,000 failure rate in the bar, we want to figure out, okay, what stress will cause our component also to have a 3 in 1,000 failure rate. We would use this equation, and you would need to know the area, effective area ratio of those two things, and of course you need to know the Weibull modulus. So that is a typical Weibull modulus problem. Okay. Next, equations for nucleation from melt and the ideas behind the questions that we may be asked about the topic. So going to chapter 11, the first half of chapter 11 is where you want to start. We walk through these in the notes. These don't include my scribbles because I was gone this day, but the notes that I posted on Canvas do have them. But essentially it talks about the things that tie into nucleation. It's a balance I mentioned previously between the volumetric change in free energy, that's making it be that positive, that makes it want to happen. Assuming that that's a negative value, then that is saying, yes, the solid should form out of the liquid. But the thing that's preventing it is the free energy from coming from the surface. So it's a balance of those two things. Hence why when you look at this, here's our net change in free energy. You can see it right here. It's got two terms. The first term, assuming a spherical nuclei for a moment and homogeneous nucleation, check it out. The first term is 4/3 pi r cubed. That's the equation for the volume of a sphere. So that volume is going to be multiplied by the change in free energy on a per volume basis. But then we're going to have a second term, which is plus 4 pi r squared. That is the surface area of a sphere multiplied by gamma, which in this case is going to be our surface energy. So that will tell you the delta G. Since both of those, the surface energy and the volume, can be written as a function of, say, r, the radius of the sphere that forms, that lets us plot these things, right? You can plot the free energy as a radius curvature. And in the notes, it would have looked something like this, where if you look at the change in the free energy as a function of r, it looks something like this, where there exists a critical value of r, which we have been calling r star, this critical value. And if you go above that value, if you can somehow nucleate a crystal that is larger than that, then it will, from an energy standpoint, it would rather keep on growing, because growing causes it to go down in terms of energy. So it will just keep on growing. But if you only crystallized a small one, and it was only, say, here, then it, in terms of free energy, actually goes down. It's more stable for it to dissolve away. So hence why we have this critical nuclei size. If you hit this critical nuclei size, it grows. If you don't get there, it will not grow. So there are some expressions where you can actually calculate that r star value and the according delta G star equation, which is telling you how high is this activation barrier, delta G star, that will cause, like, what is the activation barrier that must be overcome to keep on growing? And those are worked out for you here. Here you have them written out. You've got the equation for r star, for delta G star, written in terms of materials properties. So for example, 2 times gamma. Gamma is our surface free energy. T alpha beta is the temperature from a thermodynamic standpoint, where you would expect the transformation to take place. If this was ice forming in water, assuming no salt or anything else, then we know that happens at 0 degrees Celsius, right? When you bring water down below 0 Celsius, technically it wants to turn into a solid. But we're going to go below that because you have to account for the surface energy. So this second part accounts for that. This T alpha beta minus T, that's telling you how much undercooling is happening. So that is a positive number, because you're saying how far below that transformation temperature are we going? Is it 5 degrees undercooled? Is it 10 degrees? That's what this T alpha beta minus T is. And then delta HF is going to be the heat of transition on a per molar basis. Similarly, it's the same variables in the second equation. They're rearranged a little bit, but it's the same sort of approach. So those are the materials constants. The same sort of analysis can be applied to heterogeneous nucleation. And in fact, the only difference is that this term right here, the delta G star term, gets multiplied by a number between 0 and 1. If we scroll down to it, we'll see an example of this. Instead of forming, this is rate of homogeneous nucleation. Okay, here's heterogeneous nucleation. The only difference right here, see, it's the exact same equation. Delta G star is the same as delta G star before, except it's multiplied by S as a function of theta. And that's basically saying that instead of forming a full sphere, right, we're just forming the cap of a sphere, which changes the surface area to volume ratio. So it's essentially just less by a number between 0 and 1. And it would depend on the angles, how much of that spherical cap we include versus exclude. Okay, next I see a question about eutectic versus eutectoid versus proeutectoid and the like. So to answer that, we're going to go back to chapter 10 on our phase diagrams. On our phase diagrams, we learned about these important types of ones. I think there's a good one at the very bottom of this one. Let's take a look at it. Oh, maybe I got rid of it. Well, let's take a look at the steel phase diagram. It's as good as any. So in the steel phase diagram, let me clean it up for just a moment so we can see what's going on here. So in this steel phase diagram here, there are many of these points that are being asked about. First off, let's talk about a eutectic. A eutectic is a transformation that goes from a liquid to 2 different solids upon cooling. So where in this diagram do we see that? Well, when you start to look at it, you say, like, oh, here's my liquid. If we're going to go from a liquid to 2 different solids, clearly that happens right as you go through that bottom of that V right there at 4.3 weight% carbon, right? Because at that reaction, in fact, all along this line, you have liquid going to gamma plus Fe3C, austenite plus cementite. It happens 100% liquid to 100% eutectic composition at that point. But technically, anywhere along that line, if you have liquid left over, so for example, if you're coming down right here, just above that line, we could do the lever rule. And the lever rule, I'm just eyeballing it, but it looks like about 3/4 of your material will be a liquid at that point. So if we were to zoom in and draw a little sketch of that, it would look like 3/4 liquid with 1/4 solid, and the solid is this gamma phase. But all of that remnant liquid, as soon as you cross over below this line, technically, from a thermodynamic standpoint, all of that wants to transform nearly instantaneously to a mixture of gamma and Fe3C. And the way that it can achieve that, since it's happening very fast, is by forming these striped sort of microstructures. We call those eutectic microstructure or lamellar microstructures, but that's a eutectic point. Now, eutectoid is almost the same, except it happens at, we're going to show it right there on the far bottom left, at 0.76 weight percent carbon. So it's going from one solid to two different solids at a single point. So cooling through that transformation right there, you're going to go from pure austenite to now a mixture of ferrite and cementite. So along that line, we're going to have austenite transforming to a mixture of ferrite plus Fe3C cementite. So that would be a eutectoid reaction. Now the other ones, paratectic. Paratectic means that you have a liquid plus a solid turning into a different solid, right? So liquid plus alpha, for example, turning into beta. Well, we can see that happening right here at 1493 Celsius and about, 0.4 or so weight percent carbon. You go from having liquid plus delta phase into gamma phase. So rewriting our equation, it's liquid plus delta turning into austenite. Okay, so that's an example of paratectic. And paratectoid would just be, I don't see one on this diagram, but it would be almost the same. It would be two solids, say alpha plus beta, turning into gamma. And I don't see that anywhere on this diagram, but if we scroll up, we can find one from another diagram. Right here at that red point that's been circled right there. That red point that has been circled, just above it, you have a mixture gamma plus beta. And when you go below it, at that point, you end up with alpha. Now, sometimes people ask like, well, what about like if you go below it, don't you actually miss it? Yeah, technically you do. But at that point, you have an equilibrium upon cooling between the phases that we just described. So that would be a paratectoid. Up here would be a paratectic. Yeah, and that's what I see on that diagram. Okay. There are a few other ones I think we talked about in this class that are unusual, but those are the ones that you need to know about for this exam. Okay, next one. Can we go over how to use the stable nucleation equation? I'm a bit confused what the T represents and how to use it specifically. I think we probably answered that, but one more time, I'll just briefly say the T is going to represent the temperature that you're at right here. So here's the equation. In the equation, I think what is being asked about here, let me just note it. This right there, that T alpha beta minus T, the T alpha beta is the temperature at which you expect the transformation to happen. The T is the temperature at which you are at. So for example, on a number line, if we were to plot temperature here, and this is, say, 0 degrees Celsius, and this is like 10 degrees Celsius, and down here is like minus 5 degrees Celsius. If you are right here, then you are 5 degrees below the point at which you'd expect the transformation to take place. So that's a positive number because we're talking about this in terms of undercooling, right? So that's what the T is in that equation. Can you explain a MOSFET like I'm a caveman? This is the best. Let's talk about MOSFET as if you were a caveman. MOSFETs are amazing, so let's take a look at them. Here's a MOSFET. This is in chapter 12 notes in the latter half of the chapter when we start talking about devices. Once we introduce the concepts of semiconductors and that, now what do you do with those semiconductors? Well, one thing that you can do with them is make this kind of complicated looking diagram here. In this diagram, what do we see? Well, start in the bottom in the pink layer. In the pink layer at the very bottom, it says P-type substrate. So your base material is going to be doped to have excess holes. So this would be silicon with like say phosphorus or something in it. That's going to make it p-typed. Okay, now on top of that, you're going to have these two n-type regions. One is called your source and one is called the drain. That's kind of conveniently named. Something that goes from the source eventually will go to the drain, right? So in other words, what we would like to have happen is we'd like to have these regions which are n-typed. Because they're n-typed, we know that they're going to have excess electrons. So the excess electrons in these regions, if you were normally to try and make the electrons in those regions travel from one to the other, traveling through this region here to get to the other one, they would have to travel from an n-type region to a p-type region, and that would cause recombination, right? If we talked about that previously, it would look something like this. If you were to try and bring it over, these carriers, when they get to this p-type region, they'll just fall down and recombine and give off light. You would have made just an LED inside your electronic device. So if you want to actually make that possible, you have to do something to it. So clever people realized, hey, what if we made a thin little pathway between those two regions, source and drain, where along that pathway, it's filled with electrons, and so it stops being p-type, it becomes n-type. So how do you do that? The clever bit for how they achieved that is by applying a gate. The gate is shown up here. You have a metal. The orange area is going to be an oxide. It has to be an insulator. The reason that it has to be an insulator is that we're going to apply a voltage to the gate such that we accumulate lots of positive charge along the top surface of this gate. If that material was a conductor, then these electrons would just travel right through the gate to the substrate. But because there's an insulating oxide layer, what it causes to form is a bunch of negative charge along the bottom side of that oxide. Well, a negative charge is nothing more than excess electrons. In other words, we have created a tiny little pathway for our electrons to travel from the source over to the drain. And therefore, as long as the gate voltage is applied, you now have conduction from source to drain. And so you can use this to write information, right? Memory, like that can be a 0 and a 1. Whether or not that's conducting is your 0 or your 1 when you have a memory. So this is a type of transistor. And when you don't want them to conduct, you just remove the voltage from the gate. When you remove the voltage from the gate, then all these positives and all these negatives disappear, and it goes back to being when an electron tries to travel across here, you just get recombination, and it's not allowed. So that is, I don't know if that was a caveman explanation, but that was my best attempt. Okay, can you go over alloys versus pure metals? What would we need to know about those? You can learn about those probably starting with chapter 5, imperfections. Right here, we talked about, one of the first things we talked about in this chapter are things like point defects, like vacancies. We said it's actually hard to get a material that's totally pure without any defects. That's actually very difficult. Defects are common. They have an activation energy and they form on their own. In ceramics, we said that they come in pairs because ceramics have charge. You have a positive cation and a negative anion. So for example, if you're going to have a vacancy of one, then you have to have a vacancy of the other. Otherwise, the charge neutrality wouldn't work. So the idea behind alloys and pure metals is to start to use defects on purpose. So for example, sterling silver is a good example of this. It is 92% silver and about 7 or 8% copper. Now, adding copper does two things. It does many things. It probably changes the density. It probably changes the conductivity. It does many things. But the two important things that it does, it makes it cheaper because copper is a less expensive metal, and it makes it stronger. So sterling silver from a jewelry standpoint, it's cheaper, but it's also stronger. It's less likely to get scratched or bent or something. So this is an instance where you have intentionally chosen an alloy to achieve your end purpose. Now, why did it make it stronger? We talked about that a little bit in this chapter, but we went into greater detail when we got to chapter 8, deformation, when we started to talk about strain fields. Strain fields in materials, let me find them here. Here we are. Strain fields in materials change the way that dislocations move through a material. For one thing, dislocations themselves have strain fields. Here you see a diagram of that, where you have two dislocations. These are edge dislocations of the same sign on the same plane next to one another. So you have this extra half row of atoms, right, that's been crammed in right here and right here. And because there's extra half row of atoms, that's going to be pushing the atoms around it. That whole red region becomes compressive. And the blue region is going to actually be pulled apart a little bit. It's going to be under tension. And since these are lined up the way they are, imagine how much worse it would be if you brought those two dislocations together. Now you'd have a really big compressive region and a really big tensile region. So they don't do that. Instead, they repel one another. They move away from one another. And if they are the opposite sign, then they would be attracted to one another and they would annihilate. So how does an impurity change this? An impurity changes this because imagine what would happen. I think we have a diagram of that in these videos. If there was, yeah, if you watch these videos, we have an example of it. But let's say that you had like a really big atom in this lattice, like, so I'm drawing it there. If you had, let's imagine you had a really big impurity, you introduced some sort of larger atom there. If that's there, then this dislocation will want to come and park it right next to it because you've got this compressive region from the extra half row of atoms, then you have this tensile region, and that's being offset by the region of compression from that dislocation around it. So it does what we call dislocation pinning. It pins it in place. So that's going to change its mechanical properties. That's one example of how an alloy and a pure metal will change their mechanical properties. How does this affect LeBron's legacy? That's what I want to know. So great. How can I build a recliner with this equation? Ask for a friend. The trolling's magnificent. Is M here a given, a solve? Is M here a given / solve or a constant? So in this, we've covered many chapters. I'm trying to think all the places M has shown up. It might have only been in Weibull equation. Is that the only time that we saw M? If it was, then M is something that you don't, well, it could be given. For example, here, if I were to give you this figure, then M is given. I gave you this data, and I maybe gave you the fit, the y equals mx plus b fit. It's probably not reasonable on a final exam to give you raw data and do the linear fit yourself. You know, we do that with fitting software, so it would probably be something that would be provided. Okay. How about this one? It says, are we going to be asked about deformation of ceramics, metals, polymers at the atomic level? Will there be equations involved? We didn't do any equations, not really, for that in this class. That was more conceptual. What you're going to want to review for that is Chapter 8 on deformation mechanisms. We actually talk about them for the different materials as we go through them. So, for example, if we scroll down, first we were talking about dislocation and dislocation movement, which led to a discussion about slip systems where you get dislocation movement specifically on certain planes. And we did learn about an equation here. It's called Schmidt's law. And it was this idea of slip in single crystals, that if you can calculate the resolved stress and compare that to whatever the critical resolved shear stress, which will make it start sliding, then you can decide whether or not an applied stress will cause slipping on that plane in that direction. The math looked kind of gross, but it really wasn't too bad. It was essentially saying your applied stress, if you compare that to the resolved shear stress and you know the angles, then you can decide whether it's greater than or less than. And we showed you some examples of that. Schmidt's law is not on the study guide, so it's not where I would spend my time if I were you. But there are other things we talked about in general. So we talked about deformation via twinning, where that's a certain type of collective movement of atoms that produces a grain boundary that preserves a mirror symmetry across the grain boundary. That's different than, say, a dislocation moving. An edge dislocation inching its way through the lattice is a series of individual atoms breaking their bonds as this extra half row of atoms moves its way through. That's different than what we're seeing here, where a bunch of atoms collectively move. And the example we gave in class was that tin cry video, where you could actually hear the tin cracking, and that's the sound waves produced by a bunch of atoms moving together produces a sound wave, which we can hear, which is kind of cool. When it gets down to metals, we talked about ways to strengthen metals, for example, grain size reduction, alloying. And then when we got eventually down to ceramics, we have to get past grain growth. With ceramics, we talked about why they really just don't deform very easily. And that's because they're made up of these positive and negatively charged ions. And so if you go back to our scenario of a slip occurring, you say like, well, slip could still happen here. I could still imagine a highly packed plane and these atoms could slide past one another. The problem is that as they start to slide past one another, as you can see in this picture with the big Ghostbuster X going through it, the negative would have to be sliding past another negative ion. The positive would have to be next to a positive. And the electrostatic repulsion that would induce is just so big that it would rather fracture. That's such a high energy intermediate state that it decides it's easier for me to just cleave and break and introduce a new surface, which has a surface energy penalty, than to continue trying to deform. Polymers deform in their own crazy way, right? And here's the typical steps involved in polymer deformation. First, we recognize that polymers are very often a mixture of crystalline regions and amorphous regions. And as you start to deform this material, the amorphous ones will be the first to sort of elongate to align themselves with the deformation direction. The crystalline regions themselves can change their orientation to better get aligned. Then they can start to break up, and eventually you get breaking up entirely and orientation of the amorphous and crystalline regions. So I think understanding the conceptuals of those things is what I'm going to be asking about, and that's more in line with what you want to know. Could we review fractography? Fractography we learned about in chapter, might have been 7? I think it was 7. Oh no, that would be back in 9. Sorry, we talked about chapter 9 was failure. We learned about fractography. So an example of fractography is shown right here. In this picture, remember we were talking about the campfire. And in the campfire, one of the things they did is they actually found the smoking gun, like where the fire started. And they looked at this thing, and this thing that was still attached to the tower had broken off. And when it had broken off, you look at the cross section, this is the fractograph. And they have it labeled below. You've got like this sort of, you can see the sort of semicircle markings. These are the striations or the beach marks. There's sort of rust happening, so you know that this happened over time. It wasn't immediate. And then something happened at the bottom, circled in blue, where a different mode of fracture must have occurred. And that's where the fracture, it was happening step by step at first, and then it happened quickly at the end. So that was where brittle fracture stepped in. So understanding how you would use these, what to look for, might be useful. For example, if you had a picture of these two things, something that is flat with a little notch on the surface versus this, which has the typical cup and cone, you can right away tell one was a brittle fracture and one was a ductile fracture, right? Because deformation occurred in the ductile one. The material was able to deform and it actually sheared, hence why it's at a 45-degree angle. Whereas in the brittle fracture, once a big enough flaw was present, the crack propagated the rest of the way, all the way through the surface. You can see that in micrographs. On the left-hand side of this micrograph, you see brittle fracture because, again, it cut right through the grains. They're nice and flat. On the right-hand side, it's ductile because the crack was meandering around them, leaving a roughened surface. In ceramics, there are some special hallmarks to look for. There's usually the point of origin, and surrounding that point of origin is this mirror region. And then after the mirror region, you have these mist regions and hackle regions with lines pointing towards the spot where it failed. Those are the types of things that I expect you to understand for fractography. Can you say what a lower modulus means again? A lower modulus, if we're talking about modulus of elasticity, which is usually the abbreviation there, modulus is normally modulus of elasticity or Young's modulus, then that means that it is a more compliant material. Low modulus means it doesn't take as much stress to produce a strain, right? So a high modulus material is a stiff material, is not a compliant material. High modulus means it takes a lot of stress to achieve a strain. The relevant equation, if you were to plot stress versus strain here, if you had a material that was a really steep line here, then it's this slope that is your modulus, right? So to achieve a given strain, let's say you wanted to strain it to that point, you had to apply a significant stress compared to a material that had a lower modulus, something like this. If you wanted to get to that same strain, a much lower stress would be required, right? So that's the example of modulus, usually having to do with elastic modulus. Okay, what is stress 0 and stress F in the context of Y? Well, I think we covered this. So I'll just briefly say that those are, let's come up to them here. In our first equation, when we saw this, sigma naught was our scaling parameter, and it, along with m, are the two things that we can change in our equation to try and make our data fit this general equation. Sigma f, on the other hand, is something that's causing your material to fail. So for example, if you tested 20 samples and you tested them as a function of stress, then you're going to record the stress at which each one of those failed. So sigma f is your tunable parameter that tells me if I take and I load my stress up to something like 300 MPa, then the according value of my failure probability can be calculated once I know the value of sigma naught and m. Okay. Oh, sorry, then never mind below. Yeah, I'm sorry. We covered it then. Times like these, I wish I paid more attention in class. Too late, too little, too late. A higher Y modulus. Okay. All right. TTT diagrams. Many people Many people want the TTT diagrams and how they relate to phase diagrams. So to do that, we're going to jump ahead to chapter 11. Chapter 11 is going to be towards the latter half of that where we start getting to TTT diagrams. Yeah, right around here. So we left off, before we got to TTT diagrams, we were talking about this Avrami equation. And the Avrami equation, literally when you fit it, all it is, it's just an equation that if you're trying to plot y between 0 and 1 as a function of time, it's something that kind of is S-shaped and goes between 0 and 1, right? But what that tells you is that, oh, actually that means if I were to take the instantaneous slope, there is a point here that has the highest slope or the highest rate of transformation, right? Your rate of transformation is at a maximum at some point in the middle, and then it slows down again. Well, that's kind of the idea captured behind these TTT diagrams that produces the nose in the TTT diagram, right? Like here's that exact same thing drawn right here. So the transformation begins, and you can see that it begins. It finishes, and it finishes, and at the middle, it's transforming the fastest that it's going to transform. So if you were able to measure this sort of Avrami data at a bunch of different temperatures, right? This was taken at 675 C, so that's why they're plotting it right here at 675 C. But you could do another experiment where you do the exact same thing. You look at some sort of transformation, whether that's polymer crystallization or a eutectoid transformation of, say, austenitic steel turning into alpha plus cementite. But you do that at a bunch of different temperatures, and then you reconstruct those to form this TTT diagram, where the TTT stands for time temperature transformation. And they're really useful because they tell you, as a function of the temperature where this is happening at, what sort of transformation can you expect? Will it be complete transformation? Will it be partial? Like here you can see this diagram. They started out with a eutectoid steel, just pure austenite, hence why it's a bunch of these gammas, right? Those gammas, as you cool it, in this scenario right now, we're just assuming that you can cool it instantaneously, like you cool it instantly down to 625 degrees or whatever that is. And then you hold it, well, at about 2 seconds in, is when you get your very first transformation from pure austenite to the very first amount of coarse pearlite that's going to start forming. Now, if you hold that for all the way through to about 10 seconds, between 2 seconds and 10 seconds, roughly, you get complete transformation of pure austenite to pearlite, which is a mixture of alpha ferrite and Fe3C cementite. So these diagrams are just super useful because they're telling you not just the thermodynamics, they're telling you from a kinetic standpoint what should happen. Because from a thermodynamic standpoint, what should happen was really clear. Like if we went back to our steel phase diagram that I showed you previously, steel phase diagram said this, right? This line right there at 727 C says as soon as you go below that line, if you're just a little bit below it, technically from a thermodynamic standpoint, all of that should transform to alpha plus Fe3C. But what this TTT diagram tells you is how fast that reaction actually happens. And in many cases, you can actually quench things so quickly that you don't even observe the transformation. You prevent it, right? So the example we gave of that was with I think it was back here in chapter 10. We talked about YSZ, yttrium stabilized zirconia, sometimes called ceramic steel, because you suppress a transformation until you want it later. So here it is. In that example, here you've got YSZ. So showing you the blue lines represent the phase diagram, right? So thermodynamic lines of when something should switch from one phase to another. But what happens is, let's say you're at this tall vertical line here in the middle. If you cool it down, technically thermodynamics says around 500 degrees, that tetragonal plus cubic phase, T plus F, should switch to monoclinic plus fluorite cubic phase. But in practice, that is easily suppressed. You don't have to cool it down very fast. It is suppressed so that you end up with metastable T plus F down here at room temperature, when technically from a thermodynamic standpoint, it wants to turn into M plus F, okay? Hence why I think these are really valuable, because the phase diagram tells you one bit of information, but the TTT diagram tells you the sort of reality of okay, but in reality, this is the sort of rates that you can expect, and that's going to influence things. So here we show it for a bunch of these different steel ones. So here's the complete steel TTT diagram for eutectoid steel composition, where again, if you cool it fast enough, if you can get it from above its eutectoid temperature at around 727 C, if you can cool it all the way down below this nose, 500, if you can drop it over like 250 degrees in less than a second, that's not trivial always, then you can avoid the beginning of the transformation to either perlite or bainite. And then if you continue quenching it, then you can actually start a different transformation, which is the martensitic transformation. And we talked about that in steel. Martensitic steel is one where you get right here. On the far left, you have gamma FCC. So this is your austenitic steel. They're not showing you the carbon in that picture. But if you were to quench it fast enough that you get martensitic, then this structure actually slightly changes and it turns into this one over here, this BCT martensite. The structure actually elongates just a little bit. And so it transforms. There's a slight volume expansion, which causes cracking. But if you then anneal that, you don't get the eutectoid sort of zebra stripes. You get a very fine dispersion of cementite in your ferrite, which gives you some pretty awesome properties. Anyways, that's TTT diagrams and how they relate to phase diagrams. How about this one? It says, what do you mean by effective area on the study guide? Is that just the A bar, A component, and the Y topic, or is there something more general that you want us to know? Yeah, that's exactly what I mean. I don't expect you to be able to calculate those. I would give you those if I want you to use it. But I think understanding that Weibull, when you do it on samples with a certain volume, that you have to transform that data in some meaningful way if you're going to try and extrapolate that learning from test bars to, say, freeway overpasses. And the way that we do that is by taking that equation that has the effective area ratio. Okay, for intrinsic versus extrinsic and or undoped versus doped, so does the intrinsic mean that the conductivity equation will stay the exact same, N and P, while if it's extrinsic, depending on the type you ignore? Let's just dive in and make sure I'm explaining that correctly, because I'm not totally sure I'm following the question, but let's dive into it. So chapter 12 is when we got into electronic properties. I'm going to scroll down to our semiconductors, where we learned about intrinsic versus extrinsic. So let's start with this diagram. This diagram is showing us the band diagrams for metals, semimetals, semiconductors, 3 different types, and insulators. They're all similar. Metal has the Fermi level, which again, think of that as if you were to cool this thing down to 0 degrees Kelvin and look at the point to which your electron's occupied. Where is that level? That's the Fermi level. Now, we're not ever at 0 Kelvin. We're always above that. And if you're above that, then your electrons have a little bit of energy where they can occupy higher levels by jumping up a few seats. And the higher that temperature, the hotter your material is, the more that distribution gets blurred. Hence why you see this grayscale region. It goes from white to dark with this grayscale region. That's representing some sort of temperature effect, that these electrons are not all the way down at their lowest level, but their average level, that EF, that's the Fermi level. If that Fermi level lands in the middle of a band, you get a metal. If that's a really thin band where it lands, you get like a bad metal. Hence, we call it a semi-metal. But if that energy level lands between bands, then you get either a semiconductor or an insulator. If it lands in the middle of a really big band gap, it's an insulator. Things like alumina, right? We use alumina as an insulator. We don't want it to conduct electricity, and it doesn't because there's a really big band gap. But silicon, that's only got a 1 eV electron volt gap, so that's pretty small. And then furthermore, you can add excess electrons or excess holes, moving this Fermi level closer to the valence band or closer to the conduction band. And in doing so, you give it more carriers of one type than the other, right? If it's intrinsic, then the only carriers that get from the valence band to the conduction band are the ones that can jump across the gap. So for every electron that's created up here, it came from making a hole down there, right? So there are equal numbers of N and P, right? Therefore, it's just the intrinsic carrier concentration that we care about because they're equal. But when you dope it, P-type or N-type, you've done something. You've added some sort of other element, which we'll get to in a moment, such that you've made it so that there are far more of one carrier type than the other. You've made it so that there are orders of magnitude more holes or electrons. So now it has predominantly one carrier type, which allows us to make all the p-n junction devices that we know and love, from LEDs to photovoltaics to transistors. So how do we dope these things? We talked a little bit about that when we got down to, right here. So this is an example of an intrinsic semiconductor. You see a lattice made up of silicon, and technically it is possible to have one of these electrons that would be caught up in the silicon band get delocalized and jump up to its higher energy level. The example we gave was our, bus in England, like these double-decker buses. Technically, this electron can jump from there and occupy there, creating a hole and the hole is able to move in the valence band, that's the lower energy level, and the electron is able to move in the upper level, that's our conduction band. Both of those can contribute to the overall electrical conductivity, so we account for both of them. So if you look at the equation that arises from this, here it is, it's got both terms. The overall electrical conductivity is equal to this term, the first term, which accounts for the number of electrons, N, like that's your electron concentration, the number of electrons per volume typically, times their charge, that's absolute charge of the absolute value of the fundamental charge, times their mobility, the degree to which they are able to easily move, right? That's essentially the electron friction that we sort of alluded to. And then you have the second term, which accounts for the number of holes, right? So you have the concentration of holes times their charge times their mobility. You have to add those two together because these are, even though the mobilities might be a little different, they're both going to be important. So sometimes they'll write these two things combined, where we know that N equals P equals Ni. Therefore, you can rewrite this equation as just that with you're adding up the mobilities. That's also possible to do. But that's very different than extrinsic semiconductors. In an extrinsic semiconductor, we've now doped it to achieve something specific. So phosphorus, for example, phosphorus is a group 5 element, so it has 5 electrons. So it is going to make it N-type. Adding phosphorus to silicon is giving it 1 extra electron, which we can pretty easily delocalize. Like this electron right there, it does technically take energy to strip it away, right? If you want to strip this thing away and have it start conducting, you can do so, and it will take a little bit of energy because that phosphorus does technically still kind of want it, but it doesn't take nearly as much energy as stripping away an electron from a silicon. On the other hand, you could go the other way. You could apply a group 3 element. Since silicon is group 4, going group 3 will now give us 1 electron too few. So here you see aluminum. It has a built-in spot for an electron to occupy. So some other electron could come and occupy that spot, and in doing so create a mobile vacancy that can travel through the valence band, right? So that is the idea between extrinsic and intrinsic doping. The equation for extrinsic doping is technically the same as what we saw before, except that because one carrier type is so much bigger than the other, we just leave it off in the equation, right? For example, if N is orders of magnitudes bigger than P and N sub I, then there's not really any point in including this, is there? Technically, you should include this term, but it's so much smaller. Like this could be like orders of magnitude larger, this first term, than the second one. So we just leave it off. It's an approximation, but it's a useful one. Okay. One of the sides of the equation, yeah, I think we answered that. Can you go over strengthening mechanisms? So to look at strengthening mechanisms, you're going to want to go back to chapter 8. And I think that we sort of covered this already, but if you go back and read these, like deformation and strengthening of polymers, this would be good to go back and read through it. Like what exactly was causing the strengthening? Well, when you align these regions, what would the strength look like if you were then to keep on pulling versus how it was when it started? So clearly drawing polymers, when we make ropes and stuff out of polymers, we tend to draw them because as you manufacture it from the melt, it's actually orienting the polymers such that they are now with their strongest anisotropic direction in the loading direction of the rope. Similar things, you can look at strengthening mechanisms of metals. We talked about Hall-Petch equation, when you change the size of the grains, for example, when you orient them, when you can achieve, you can make it harder for the dislocations to move by either adding dislocations, right? So that's cold working. By reducing the grain size, that can also be accomplished by cold working, or by adding dopants, defects, right? Impurities. All those things are all things that you're going to want to go back and review. When sketching microstructures, do we need to convert from weight percent to volume percent to have a correct sketch? Oh, that's a really good question. If I ask for it, then yes, but if not, then you can just approximate that the area fraction, which is what you're drawing, is proportional to the value. Like that may not be the case, right? For example, here, I did that right here. I said like at that point, right here, I'll just draw it again. At this point right there, it looked to me, just eyeballing it, that it was about 3/4 liquid. Well, what if the density of the liquid is like wildly different than austenite? Then technically you'd have to figure out what you could calculate the volume fraction from that if you knew the density. That's more work that I'm going to expect you to do. A simple sketch suffices, but for a complete answer, I'm always going to ask for what is the fraction of the phases and what is their composition. So coming back to this example, at that point just above there, the fraction of the phases we would get by taking the lever rule. So let's go ahead and do that. The lever rule at this point, right, we're going to take this portion and divide it by the total portion. So that's going to be 4.3 minus, it looks like we're at like, call it 3.75. So 4.3 minus 3.75, and divide that by the total distance, which is 4.3 minus 2.14. That would give us the amount of solid austenite. Now, taking 3.75 minus 2.14 as the numerator would give you the amount of liquid. So you would actually want to calculate it, and that would tell you the amount of the austenite phase and the amount of the liquid phase. But their composition you get by looking left and right and seeing where the tie lines are. Like this guy's right here, this one's right over here. So the liquid is going to have a composition of 4.3 weight percent copper. The austenite is going to have a composition of 2.14 weight percent carbon. I think it said copper, but I meant to say carbon. Okay, so you need both of those. How many note sheets are we allowed? What's the starting time? Good question. So the exam is tomorrow at 1 p.m. and 4 sheets. Yeah, somebody already answered it. Can we go over fixed second law for mass transport? An example problem that you could use for this. Yeah, so with mass transfer, that's going to be chapter 6 when we talked about diffusion. And here it is. So the idea behind fixed second law is that it is now time dependent. If I ever say that something is steady state, not changing with time, constant, then you're going to be using fixed first law, right? Fixed first law assumes that the parameters aren't changing. For example, whatever's causing your material to diffuse through the membrane, it's not changing. It's constant over time. But if it is changing over time, like it was nothing and then you put it in solution, you bonded things together and then you put it in a furnace, now they're going to start diffusing. That is definitely, those are all keywords that you're going to be using fixed second law, which is going to be non-steady state. It's going to change with time. Like here you're seeing in this diagram here, you're looking at the concentration versus X. That's what we call a diffusion profile, right? It's showing you how the material is diffusing into the material X. So it might be at first at some low time, it looks like this first line over here, right? This line right there is like at time t equals 1, some short time. But as you take it towards time t equals infinity, maybe it approaches that linear line, which by the way, the linear line would just be fixed first law. So fixed second law, as it approaches steady state, the equation starts to look more and more like the steady state equation, right? If we go back to our fixed first law, it was a straight line, right? And the slope of that line was proportional to the diffusion coefficient, right? So that's what we are moving towards as you approach steady state. But if you're not at steady state conditions, then you still need to know what the diffusion profile will look like. And the way that we do that is with this equation. Now, we talked about it in class that this is just one potential solution of the many that are out there. This works for very specific conditions, which are described here, like X equals 0 is your surface. Their time t equals 0 is when diffusion begins. We assume that the concentration was fixed all the way through material at C naught all the way through, and then the surface is unchanging. Like those things may not be the case for the engineering scenario that you're working on, but they are, for a lot of instances, an okay solution. So, or an okay approximation. And if those boundary conditions work for you, then there is an analytical solution that you can use. And we didn't derive this in this class. When you take partial differential equations, PDEs, you will learn how to derive this, but that doesn't mean that we can't use it. So in this equation, C sub X represents the composition at any point X. Like coming back up to this picture, let's say that you're at this time curve, like that right there, that is my C sub X, where the value of X is 2.8 or something. If you plug in 2.8 for X, then you get out the composition, or the concentration, which is 0.2 of whatever those units are. Okay. C0 means the concentration of that diffusing species that already existed in the material. So in this diagram, that looks like it's 0. It's all approaching 0, right? There was initially none of this concentration. Oh, it's actually because it's been normalized by it, right? But maybe you had a material where if you're plotting like the raw concentration, maybe it actually looked like this because the baseline concentration in your material was really high already. And you're adding more for sure, but the baseline was high. So that's what that C naught is it's showing you what the composition is deep in your material. CS is the concentration at the surface. So in this diagram, that is CS up here at the top. At the surface, maybe because you painted it on, or maybe you did ion implantation, you got high concentration at the surface. relative to what it was deep within the material. And by the way, that can go the other way too. If you somehow removed material from the surface, if you were down here, you can still use these exact same equations to look at a negative diffusion coefficient, diffusion profile, I mean, totally the exact same math. That is all equal to the right-hand side of this equation, 1 minus the error function of x over 2 times the square root of dt. X is going to be your distance from the boundary that was defined here. X is a positive number going into the surface where diffusion is happening. And then d is your diffusion coefficient, t is your time. We learned about diffusion coefficient previously. It was right here. We said that d, the diffusion coefficient, is a thermally activated. It's thermally activated because as you get things hotter, you're giving them more thermal energy to travel through the material. And so it makes sense that you have this d is equal to d naught, some pre-exponential times the exponential with a negative QD over RT. QD is going to be the activation energy for diffusion. R times T is going to give you your thermal energy. So it's something that depends on temperature. But if you know the temperature at which this fixed second law thing is happening at, then you can calculate this fixed second law equation. Okay. Fixed second law, yep. Diffusion. Can you go over crack growth and Bragg's law? Yeah, let's do that. So crack growth came way back in chapter 9. There were several interesting things we learned about in chapter 9. The first thing we learned about was just Griffith's fracture theory, which was this whole idea that there exists a critical flaw size. And if you know your fracture toughness of your material, then you can actually calculate the flaw that will cause that to break under a certain stress condition, which is pretty rad, right? So right here, you've got K, which is our stress intensity factor, right? Sorry, excuse me, I said that wrong. K here, yes, it was derived from comparing it to stress intensity, but we're going to call this our fracture toughness, K1C, is equal to Y, a dimensionless geometric parameter, times the stress that is being applied multiplied by square root of pi A. So A is our crack size, it's the half crack length. And essentially, if K is a material property that's not changing, Y is something that is geometry dependent, then you can figure out exactly for a given stress what will cause this right-hand side of this equation to be larger than the left and therefore will cause it to fracture. You could achieve that by having a really low stress but a big flaw, or a really high stress and even a small flaw. Either one of those could make the right-hand side bigger than the left, which will cause brittle fracture. So that was the first component that we learned about. And then we took it further. We said but just because it doesn't break on day one doesn't mean that it won't break eventually. And that's because cracks grow. So here's an example of how a cyclic loading condition, say stress compression, might actually cause these things to grow over time, and that could cause it to break. So we can actually learn about the rate of crack growth. We did, if we scroll down a little bit to the latter half of this chapter, we started seeing the crack growth equations. Yeah, check it out right here. So this is showing you crack length A plotted against number of cycles. And there's 3 different data sets here, triangles, plus signs, and circles. And those correspond to different stresses, right? So if the stress amplitude, like that ratio, the difference in stress is increasing, then your crack's going to grow a lot faster. It'll take fewer cycles to get the same crack elongation, right? But what is common between these different stresses is that they are all nonlinear. They're all power laws. Therefore, you need to fit them with something nonlinear. The equation that we use is called the Paris law. So dAdN, our crack growth rate with respect to cycles, is equal to big A times delta K, our range in the stress intensity factor, raised to the n, where these values A and N, sometimes the literature calls those C and N, I apologize, that's just what it is. But those are material dependent constants that you can look up, right? Once you know those, you can understand how a material is going to fail during that region 2 of its cracking. Like initially a crack will grow and that's region 1, but once it has this sort of steady state growth, well, it's not steady state, but it's growing at a predictable rate, that is what we learn how to model with this crack growth equation. And I'd say it's straightforward. The math is not too bad. Essentially, they took the same equation as before, dAdN equals A delta K to the N, where delta K is just from our Griffith fracture equation from before. And all we're doing is we're going to separate the variables, dA and dN. We're going to put those on 2 different sides of the equation. And then we're going to integrate both of those from the beginning of the crack, whatever it was when it started, A naught, all the way to the largest that the crack will be when it fails, our critical flaw size, AC. On the right-hand side of the equation, that means that we're integrating from no cycles till failure all the way to the number of cycles at failure. That sort of assumes that 0 cycles starts at region 1. We're not accounting for any cycles that occurred during region 1 crack growth. If you guys take a more advanced fracture class, you'll learn how to model region 1 and 3. In this class, we only model region 1. But it's still pretty useful because that turns out to be a big portion of the time over which crack growth occurs. And integrating these, while it looks bad, it's actually not that bad because most of the stuff comes out of the integral. Technically, all this stuff, a delta sigma to the n, n to the, or pi to the n over 2, all that for sure comes out, leaving you with just a to the n over 2 and y to the n. If your crack is never going to grow way big relative to the component, then y to the n can also come out of the integral. But technically, y does depend on a. We learned about that previously. Right? Up here, we learned that right here. Technically, y is a function of a, right? It has this sort of dependence. But if your crack never grows very big, then you can just take it out of the integral. So we learned how to use that equation. You could ask lots of questions with this type of equation. Like, for example, I could say, here's the crack growth data. You tell me if a crack starts at this size and it has this fracture toughness, how many cycles will it survive until failure? So to answer that, you know what A naught is. You're trying to solve for NF. Therefore, you need to know what AC is. AC you can learn, though, from your Griffith fracture equation. If you're given the fracture toughness and you know the stress conditions, well, you can solve for AC. So this is solvable. It is mathy. I'm going to try and make this final exam have more conceptual questions and than some of the other ones, but there still will be some math on there, and this is an example of something you need to know how to do. So that is crack growth. You also asked about Bragg's law. Let's talk about Bragg's law over here. Bragg's law, Nobel Prize was right here. This was it. Basically, Bragg, father and son combo, realized, hey, if light comes in and it is sort of like a laser in that it's an X-ray laser, you've got X-rays that are coherent. They're all in phase with one another. As they impinge upon a crystal, some of those wavelengths might hit the top surface of your material, right? Those atoms will cause it to specularly reflect. So they come down and they reflect at the same angle. That's reflection. But some of them might miss that first angle. They might not hit the atom, and they might hit the one below it. So technically, they travel this extra distance. I'm going to highlight it here. They travel that extra distance in blue and this extra distance in blue. And that extra distance, if that happens to be the same distance as the wavelength of your material right here, if you added those two things together, if they're equal to the integer number of your wavelength, then it will be in phase as it leaves. If it's in phase, right, if these things are back once again in phase with one another as they leave, then you will see it. If they are out of phase, right, if it's going like this, you won't see any light. That will destructively interfere and you won't see any signal come out. That was the entire Nobel Prize, is basically just working out the little bit of geometry that made that happen. They said, okay, if you know the angle and you know the separation between planes, then you can actually calculate what exact angle will cause constructive interference as opposed to destructive interference if you know your wavelength. That's it. That's all this equation is, right? Like, it's just basically saying like some integer number of your wavelength times your wavelength basically has to be equal to those two blue line segments. And the way that you calculate those two blue line segments is 2 times the d separation times sine of that angle. Just a little bit of geometry gets you there, right? Like this also becomes theta. Therefore, if you want the opposite angle, the opposite is equal to the sine of that angle times the hypotenuse. The hypotenuse is the d. Like, that's it. That's a really simple bit of math that produced the Nobel Prize, but it's really useful for us. So in practical terms, the way that we use this, spacing for materials is the most common way. Like, you might, for example, have this. Like, you might measure a material. This is for some material. And you're seeing the intensity. This is the intensity of the X-rays that come out as a function of the 2 theta, right? So as you shine light in, and it specularly reflects, like here's your theta, here's the reflected theta, hence that's the 2 thetas is where that comes from. X-rays come in, X-rays come out, but you only see a reflection at certain values of 2 theta that satisfy Bragg's law, where again, lambda is equal to 2 times the d spacing times sine of theta. Okay, so because your material has like specific thicknesses that are periodic in it, right? This d spacing is something that you can now query in your material. So these different peaks, here we see 1, 2, 3, 4, 5, 6 different peaks. Those would all represent different peaks that exist in your material. Like maybe this is like the 100 reflection distance, right, between the 100 planes, and maybe this is like the 110 distance, and it's smaller, right? So the biggest d spacings are over here. This is where your larger d spacings are. And then on the right is where you have your smaller d spacings. But the fact is that your material is going to have a fixed number of these reflect planes, like distances between planes, that will cause reflection. And we leverage that to then characterize materials, because you can calculate where they ought to be. For different material systems, here's the kind of nasty looking equation table here. It shows you how you calculate that d spacing for any given HKL plane. The simplest is this cubic one, right? If you know what the H, the K, and the L are, you plug them in, you square them, you divide that by the lattice parameter of this material, and that will tell you what the 1 over the d spacing squared is. Similarly, you can calculate it for orthorhombic, tetragonal, hexagonal, cubic. In this class, I want you to have these 3 equations on your note sheet, because I could ask you any of those 3. These ones are all a lot harder. I'm not going to ask you to do that on a midterm or a final, but it's something that with an Excel spreadsheet or something, or some sort of Python software, you could easily calculate those as well. Not that big of a deal. The only other thing that we talked about in X-ray diffraction is that technically not all peaks reflect, and we didn't learn about why that is in this class. You'll learn about that if you take our materials characterization course in our class, which I think everybody would love. But there you learn that there's these kind of funny sounding rules. Like, for example, in a BCC material, you only get reflections if your H plus K plus L is equal to an even number. Whereas for FCC, if your H, K, and L are either all even or all odd, then you get diffraction. So based off of that, we did a bunch of examples of how you could calculate what peaks should happen first. And that's just by realizing that your first peaks should be the ones that have the larger d spacing. And since you have only finite values of H, K, and L that you can test based off of conditions given, you can figure out which ones would come first. Okay, good morning from India. Good morning to you. I love teaching all over the world. That's pretty rad. Somebody says, on the topic of crack growth, flaw size growth over fatigue loading, does this relate to creep and SN curves? No, these are different phenomena, but that's a great question. I mean, maybe SN curves, probably SN curves relates to, let's jump back to chapter 9 and we'll show you this. So SN curves are this idea of, as you load something over and over time, they get weaker. They get past it. Where's our SN curves? Right here. So yeah, so it's sometimes called the fatigue limit, right? Some materials have a fatigue limit, and some materials don't have a fatigue limit. The example we gave in class is steel and aluminum, shown here. If you look at like whatever your stress amplitude, right? You're doing some sort of oscillating stress condition. Steel will get weaker and weaker. This 1045 steel, this one will get weaker and weaker until a certain point that is called its fatigue limit, 300 megapascals. And then you can keep on cycling that thing as long as you want. It's not getting weaker, right? It's gotten as weak as it's going to get, and then it's done. Whereas aluminum, most aluminums will just continue to get weaker and weaker. And the example we gave was the paper clip, where we just flexed it until it eventually broke. So what's probably happening is that as you're flexing it, it is related to crack growth. Is that as you're putting this oscillating growth on it, you're causing a crack to slowly grow over time until it gets big enough to satisfy the Griffith fracture equation. And then at that point, you get brittle fracture. That's very different than creep. Creep is something different. Creep doesn't have to do with crack growth. It just means that your material is deforming slowly over time. And the example we gave was bookshelves and roofs of buildings where, technically this bookshelf, heavy laden with all those books, on day one, it probably wasn't drooping like it clearly is now. But over time, that deformation happened. So what that means is that the mechanism whereby deformation is occurring is just a slow one. So if it's slow, then it's something that you need a different equation for. You can't technically just, like previously we said that we've got this equation, we have stress, we have strain, you have this really simple equation that says like the amount of rise over run modulus is equal to this over that. So if you wanted to solve for the strain, then it's simply equal to the stress multiplied by our modulus will tell you how much strain you get. What this is essentially saying is that, that's time dependent. it's really like stress as a function of time multiplied by our modulus is going to equal to our strain, which will be a function of time, right? It's happening slowly over time. And you can see that in the type of plots that are curved. Like, for example, first on day one, when they first applied that if this is time t equals 0, this is like that initial strain at time t equals 0. But then that strain grows over time. And what we learned how to do in this class was model this secondary region, which we call our steady state creep strain rate region. Okay, and the equation for that, the strain rate is constant. See, this epsilon dot means the rate, that's dE dt. It's not that it's not increasing, it's that the rate is not changing, right? So it's, and then the equation that we use to fit that is this one, where we say that the strain rate is equal to K times sigma to the n exponential of negative Q over RT. Before we go way into this, I'll refer you to the other videos that we've done previously because it's not something that is on the final exam, so I'll skip it for the sake of time. But it's a different process than crack growth. It's just slow deformation. There's different mechanisms that you can learn about. Free and donation, that's so rad. You don't need to do that. You don't need to do that. That's really nice of you, though. This is the first time I've ever done a live, so it's kind of fun to do it on YouTube. That's really nice of you. Can you go over diffusion profiles? Yeah, I think we kind of have already, but let me just briefly say a few more words about them. If we go back to chapter 6, diffusion, you can see them. So here's an example of one, right? So if initially you had copper and nickel and you just put those two things together, you welded them with no heat. Imagine a scenario where you could weld them with no heat, right? You just stuck them together. But then you put them in a furnace and you heat it up so now diffusion can happen. Well, entropy says the copper and the nickel want to mix together. And so if you could take like a scan along the material this way, you'd see that the concentration profile is changing. Before it was like a step function, like it was pure copper, no copper. But as you heat it up, you're going to start to see that the profile changes. And as you heat up for longer and longer, obviously, eventually it would just be like an even mixture. It'd be like 50-50. The entropy says, I want this thing completely mixed perfectly, but it's going to take a really long time to get there, right? So in the meantime, at time steps between that, we can actually observe the concentration profile and see what it's doing. So here's an example of one. Here they've got whatever this material is, and you can see as they do a line scan through it, this like light purple, that's our chromium. Looks like this first region on the far right is chromium rich. And then that really falls down to an intermediate. It's not zero chromium. It's an intermediate compound that has chromium. And then over here, it gets even lower. Meanwhile, you see kind of the opposite with this darker purple. This looks like iron. It's mostly iron on the far left. And then it's a little bit less iron. And then the iron plummets down here. And nickel, you can kind of see similar trends. These are all concentration profiles or diffusion profiles. XRD is up above. How would the microstructure look if it were two solids instead of a solid and a liquid? I assume that's asking with respect to phase diagrams, if it was two solids instead of a solid and a liquid. So let's go back to our phase diagrams and look at some of the types of transformations that you could see. Let's go to, where was that diagram we just showed? This one right here. Okay, so like, let's say that you are right here above that point and then you cool it down. So just above that point, just above it, you could do the lever roll. I'm approximating the lever roll and it looks like the gamma phase is maybe 2/3 and the beta phase is 1/3. So if I was to draw the microstructure, I would say that it would be, well, before you draw it, I think it's helpful to draw what it came from above. So as you were cooling this down, just above that point, let's draw that one first before we do this one, so it'll help us get it more accurate. So right here, at that point, we have about 80% gamma and 20% liquid. So you've got mostly solids that have formed this gamma phase and just a little bit of liquid left. This is mostly gamma and a little bit of liquid. Again, you would do the lever rule with actual numbers if this is an exam. But then as soon as you go below that value right here, well, the little bit of liquid that's left undergoes a reaction, right? It's going to transform to the beta phase. So that's going to tell us what the microstructure essentially looks like here. It's not going to be a eutectic transformation because it's not two different phases, just one phase. So it's basically going to say like we still mostly have these regions from before, but now you've got beta phase here and gamma there. It will not be this lamella one because it didn't transform to a two-phase region where the liquid had to switch to two phases. This time the liquid just switched almost exclusively to the beta phase. Those pro-eutectic globs might have to shrink a little bit, but it won't have to change that much. So it's going to be more or less the same. And then when you go to this point A, that's when you get this transformation to now just a single phase region, which is this alpha phase. Okay? Hey chicos, salen por favor. Salen por ahí. Okay. So I hope that answered your question about how two solids would look. Can you review error function tables? Yeah, we can do that. Error functions we introduced in chapter 6 with diffusion. If we scroll down to this, we learned about them right here. So the error function tables we use simply because that's the mathematical thing that allows us to basically get this S-shaped curve, right? When you do these diffusion profiles, it's these sort of bent curves. The error function is a pretty convenient way to achieve that shape. So the way that we can do that is by using these error function tables where the value inside the error function we're going to call z, and then the error function of z is given. And if you get lucky enough that the value of z, let's say that you know what x over the square 2 square root of dt is. Let's say you know what that is, and it happens to be, I don't know, 1.3. Well, then your life is easy because you can just look up the exact value for the error function of z. It's just 0.934. But what if you do? What do you do if you plug this in and it's equal to 1.31? Well, then what value do you use, right? That's when you need to do a linear interpolation, right? So the linear interpolation is what you're going to have to do that. So there's different ways you can do that. I think the one that I gave you in this class is that, oh gosh, do I have it here? I don't want to get it wrong. I think it's like this. You're going to take, I don't want to get this wrong. Let me pull up the notes because I don't want to mess it up in the middle of this review. So we'll go to this year's course and we'll go to our course notes. I'm going to go to chapter 6. Oh, I don't have it here. I took it. Oh, that's right, because I was gone that week. So let's pull it from a previous year when I taught this class. Chapter 6. Oh, not that class either. Let's go back to the COVID year. Okay, right here. So let's scroll down so I get the right equation so I don't mess it up. Right here. There it is. So forgive the slowness here. Here's what we're going to do. So in this case, y and x could be written as, say, x could be z and y could be error function of z, for example. The y0 would be the value that's below it, like the lower bound value. y1 would be the upper bound value. So in this case, y0 would be 0.934. y1 would be 0.9523. x0 would be 1.3, the lower, z value. x1 would be the upper one, 1.4. This allows you to solve for any arbitrary z or error function z value. So definitely practice that. We've got some solutions from former homeworks where you can see that implemented. Okay, would you rather have 500K or dinner with Jay-Z? I would take the money. How many questions is the final? Okay, the question is always 6. It's worth 300 points total, so that's 50 points per question. They are all 50 points apiece, but some have like 5 parts and some have 2 or 3. You'll see that the points are proportional, so an easy short answer question might only be 10 points. A harder one with a calculation might be 30 points. How will you curve the exam work? I don't know. No guarantee on the curve on this one. I will curve it if the scores are really bad, but I typically try not to curve the final very much. I make it easier. What will dA reduce to in the crack growth equation? dA. So if you come back over here to chapter 9 on failure and we go to crack growth, let's take a look at it. If we scroll down to when we learned about crack growth, where is it? When we separated the variables and integrated both sides, right here. Okay, so once you've gotten to this point where you've got dA, well, what's the integral of 1 over x dx? the dx goes away when you take the integral from your initial x value to your final x value, right? The dx just disappears. So you say, what does it reduce to? It goes away when you take the integral, and you're just left by plugging these values into the x there. Asking the real questions, yeah. Any other graphs that we should know how to interpret? No. Can you go over Gibbs diagram with derivatives? Yeah, we can do that. Let's hop over to chapter 10. No, chapter 16, excuse me. Chapter 16 is where we learned about thermodynamics in general. So the main thing that, again, a lot of this I sort of asked you just to take my word for it. We said that there's enthalpy, which is a measure of your internal energy, plus PV, which is the work that it's doing on the system. But that doesn't account for everything. DG would be a better term, because this enthalpy is not everything. It's basically a measure of bonding. And we can measure the change in enthalpy if you measure the dq, the heat going in and out of it, plus VDP. So in other words, if the pressure changes, this is the work done on the surroundings. This is convenient because in lots of instances in engineering, pressure does not change. So that whole term goes away, it goes to zero. So DH is simply equal to DQ, the heat going in and out. But if that's only telling you the heat going in and out, what about entropy? Entropy is the other thing you have to consider. So we need a term that combines both of those together. So that is Gibbs free energy. Gibbs free energy combines enthalpy and entropy. You've got delta G equals delta H minus T times delta S, where delta H is your enthalpy and delta S is your change in your entropy. So that will ultimately tell you whether a reaction happens, right? That'll tell you between reactants and products. If you step down, then that was a negative change in energy. Thermodynamics says it should happen. It doesn't say anything about the size of the intermediate step. As you go from reactants to products, maybe the intermediate step is so high that kinetically it doesn't ever happen. The example we gave there was diamond, right, turning into graphite. Technically, diamond wants to turn into graphite. It is a negative change in the Gibbs free energy. But from a practical standpoint, the intermediate step must be so high that it is kinetically limited. So it's a metastable material, diamond is, that we can, make rings out of, and they don't turn into graphite. So that's where we first introduced the idea of Gibbs free energy. And then later in chapter 10, we applied it to phase diagrams. And the example we gave was water. Here you see pressure versus temperature for pure water. Pure water means that it's a single component system. It's only H2O. It's not like water plus salt or anything. It's just pure water. And in this one, you can actually start to estimate why these different things happen. Like, for example, at this green horizontal line, let's say that represents Salt Lake City, right? Which has a lower pressure than LA because we're higher in the mountains, so we have lower pressure. So that tells us why the solids actually they melt into a liquid at a higher temperature, and why liquids boil at a lower temperature. This is why when you bake a cake or bake cookies or something, it'll sometimes say this is at sea level. For every 1,000 degrees above, you have to cook it a little bit longer or something like that. Because literally the temperature at which the water is boiling at inside as you're baking that cake is hotter if it's at room temperature. If it's at sea level. But if you're in the mountains, it's just not as hot. And so you have to cook it for a little bit longer, right? So where on earth did these things come from? I think the question that you were asking had to do with that. So sketching the slope of your free energy versus temperature or free energy versus pressure came from an understanding of our free energy expression. We said that G equals H minus TS. And so if you wanted to take dG dt, the derivative of free energy with respect to temperature, since the first term H has no temperature in it, it's gone. And since the second term only has temperature times entropy, then the derivative is really easy. It's just negative entropy, right? So it should be proportional to the negative entropy. So gas phase is going to have a much greater entropy than solid or liquid. So it's going to have the steepest line, and it's a negative line because it's proportional to the negative entropy. Liquid is typically going to have a greater entropy than a solid, right? And solids are going to have your lowest entropy, so it's going to be the most like a flat line. And then we realized that, that allows you to go from, there's this intersection here where solid is your lowest free energy in this region to the left. In the middle, you have your liquid is the lowest region. And then over here to the right, your gas is your lowest one, right? That's your lowest free energy phase. So then you could say on my diagram, where do I see that? Where upon increasing temperature, I go solid, liquid, gas. So upon increasing temperatures right here, we go solid, liquid, gas. Anywhere above the triple point, we see that happening. So that sketch of our unary phase diagram works anywhere above this triple point in terms of higher pressure. If you go to lower pressure, then it would go directly from a solid to a gas, never seeing the liquid phase. So what does that one look like? That one looks like this, right? That's this one right here. It went from a solid region to a gas region. The liquid line exists, like that's our liquid line. It's just that at no point is it the lowest free energy phase. Okay, so that's where this came from. That was drawing dg dt. dg dp would be similar. The integral is even easier. dg dp, this first and second and third terms, the only one that has pressure is the second term, and it's only multiplied by volume. So when you take the derivative of that second term with pressure, you're just left with volume. So in this case, the slope is now going to be proportional to the volume. For most materials, your gas is going to have a higher volume, the highest volume, followed by liquid, followed by solid. Water is an unusual one. Water kind of breaks the rule. The volume of water in a solid phase is actually larger than a liquid, hence why ice floats. It has a lower density, has a larger volume, therefore a lower density. Ice floats. Metal is not that way. Most metals sink. There are some exceptions. Silicon floats, a few other oddballs, but most of them would sink. But that allows you to do the exact same sort of things. And that's why you see when you increase pressure, the behavior that we see here, right? Where it goes from gas to solid to liquid. That's because we're going from gas to solid to liquid. These lines have been sketched at that temperature. So I hope that answers that one. Will the exam be more conceptual? For sure. I've intentionally put more short answer conceptual ones on this final than on your midterms, which were a little more mathematic. There's still math on the final. Don't be confused. There will be some, but there's more conceptual questions. This one, I'm confused on how we keep materials in certain phases and how they can be operational if they need to be kept at certain temperatures. Then it's your phase diagram, tells you everything you need to know, right? So let's say you've got this phase diagram, right? Whatever this is for boron bonded to tungsten, so tungsten boride. So if you need a material to stay in a certain phase, like your boron tungsten, look how these are really high melting point materials. These are what we call refractory alloys. They melt at crazy high temperatures. If the whole point is because you need it to not melt, the phase diagram tells you, right? It tells you, like if you are pure tungsten, you can take it all the way up to 3,422 Celsius. That's got to be one of the highest melting point metals that exists. But if you make a boride out of it, like a 50-50, like tungsten boride 1-to-1, then this phase diagram tells you that, oh dang, if I'm exactly at 50-50, I can't go above this 2665 temperature, because if I do, it's going to melt. And the closer I get to that, the more I'm at risk of local fluctuations causing part of it to melt, right? To say nothing about its mechanical properties, which typically soften, right? The modulus goes down usually. Fracture toughness actually goes slightly up as you go up. But like material properties change, but the phase of matter, which if I understand your question, can be interpreted from these phase diagrams, which is why they're so great, why we learn about them. This one says, could you review strengthening mechanisms and alloys versus pure metals and how alloys might affect? We did that one, so I'll be posting this. You can go back. That was one of the first questions that we had. And then what do we need to know about the three sustainability's three pillars? So if we come back to our chapter on sustainability, the main thing that I want you to be able to do here is for some sort of technology, you should be able to describe pros and cons, right? Both. With respect to the impact on the economy, like what's the economic impact of whatever the technology is, what's the impact on the environment, our ecological impact, and what would be some impacts on society. So I'll be able to, I'm going to be asking you to think creatively and broadly about the many different ways that any sort of new technology impacts the world around us, for better or worse. How about this one? How does supercooling work? I know it's cooling below a transformation temperature without something happening, but how do we prevent the transformation from occurring? So in this case, you're not actually doing anything. What's preventing it from happening is thermodynamics. And you're like, well, thermodynamics says, we call this whole chapter kinetics, but it's actually driven by a simple thermodynamic argument. And that is this one right here, that the overall change in free energy, which tells you whether something happens. Like, so this is like thermo. This guy right here, that is thermo. Thermo is like, tells us when something happens. the phase diagram doesn't take into account the shape of the particle that's nucleating. And the shape of the particle could totally change things, because let's imagine that it's a cube for a minute, right? A cube versus a sphere. These have very different ratios of volume to surface area, right? This volume to surface area ratio is different for a cube than it is, say, for a sphere, and that would be different than an octahedra or any other shapes. So what chapter 11, our study of kinetics, allows us to do is understand that thermodynamics just tells you on a per molar basis what should happen, but when you actually make a shape that is actually going to undergo this transformation, it's going to create a surface. That surface has an energy, and we can include that in the calculation, and what it does is it shifts our values a little bit. It allows us to, if we're cooling down, for example, from a liquid to a melt, from a melt to a solid, you can actually go below the line from your phase diagram by a little bit, and sometimes a lot of it. Some of these like metals that technically they melt at like 1300 C or something. I think we gave you an example. I think we've got it here. Let's pull it down. We did an example of this. Yeah, right here. So pure gold melts technically at 1000 Celsius roughly, but you can cool it all the way down to 230 degrees below its melting point if nucleation is homogeneous. Now, if you've got seed crystals or the sides of the vessel, then now it's heterogeneous nucleation. You probably won't be able to achieve nearly as high of a value of supercooling. But for some things, supercooling can be really significant. And I think I was gone this year. I was at a conference this year, but normally when I'm teaching this class, I bring in water that has been supercooled. So it's actually at like -4 or -5 degrees Celsius. So technically it is supercooled, and the only thing preventing it from crystallizing into ice before your very eyes is that it needs to get over that activation energy. And so in class, I'll take that bottle that's been supercooled and I'll whack it against the counter, and you can see the ice propagating all the way through the material. You can go to YouTube after this right now if you want to take a look at it. Pretty cool. But again, all you needed was that seed nucleation site. Okay, nucleation from melt. I think we went over it, but it went over my head. Is that when we observe both homogeneous and heterogeneous nucleation during supercooling? No. Nucleation from melt can happen either via homogeneous nucleation or via heterogeneous nucleation. So the picture in your mind that you want to draw is like, let's say that this was all molten, whatever, gold, right? So it's all in the, let's call it the alpha phase is the liquid, or let's just write liquid, right? That's our liquid phase. Your nucleation can happen by one of two modes. It can happen right in the middle of the liquid, like it can form a little sphere of solid, right? Or it could form along a surface, right? Or maybe you have like an impurity in it and it forms along that one, right? All of those things can happen. When we talk about homogeneous versus heterogeneous nucleation, this one is homogeneous, and the other two would both be examples of heterogeneous nucleation. That is the difference there. And what it really boils down to is your volume to surface area ratio is changing. We talked about here that if you make a cube versus a sphere, it's a different volume to surface area ratio. So what if you're nucleating just the top part of this because it's growing along a surface? Well, you have yet another different volume to surface area ratio. But it's the same thing happening in all scenarios. You have a liquid turning into a solid because free energy on a per volume basis says, let's do this. But the difference is that because the surface area is different for these different types of shapes that can occur, the energy barrier is also different. Okay, someone says, could I upload sustainability chapter notes to Canvas? I don't see them. Oh yeah, if I didn't do that, then I can upload those. I think they are before class. After class, I don't know if we did it after class, but anyways, I can check that. In a few thought out sentences, explain who would win, grizzly bear or gorilla. Grizzly bear, hands down. Although gorillas are pretty nasty too, but you got to give it to my boy the grizzly bear. And why? Because they're massive. What if you told is the first? Yeah, we'll not be telling you the first 6 questions. Okay, we are at 20 minutes left, gang. Have you still got questions for me? Drop in the chat. Otherwise, we will wrap up. I imagine there's still a few questions though, as my wife tries to fish our 3-year-old out from under the table so she can put her to bed. Okay, any other questions? Let's scroll back up to the study guide. So these are all the things I think we've covered everything here. Yeah, I think we've covered everything. Will the exam be in the same order as the study guide? Pretty much. Yep, it pretty much is. Oh, there's one more thing I put on the study guide when I finished the exam, which is glasses, realizing that the same material like silica can exist either in an amorphous state or a crystalline state. So for that, we talked about at the end of chapter 3, we talked about amorphous materials. So glasses can be amorphous or they can be crystalline. Here's an example. Silica can be quartz, and that's an arrangement of these SiO2 building blocks that are, I guess, SiO4 building blocks that are connected by corner sharing, and it makes this periodic crystalline lattice. Or you can have this amorphous material where they are, on average, 6-membered rings, but some of them are more. Like this one's got like 1, 2, 3, 4, 5, 6, 7, 8, and some only have 4, right? So on average, the rings are still 6-membered rings, but we lose our translational symmetry. They have changed, right? So the way that we achieve that in soda lime glass, right? Soda lime glass has Na2O, CaO, and SiO2. You intentionally add the soda and the lime to disrupt this lattice. We call them network modifiers, right? These network modifiers, they break up the lattice. They prevent it from forming this nice crystalline one. They break it up. Other things you can add would be like boron oxide, germanium oxide. Those also work. But that's when you talk about soda lime glass, that's what we're talking about there. Other questions I'm seeing are, let's see, future engineer right here. Heck yeah, Marco Diaz, well done. How much of the final will be one material past, how much of the final will be one material past the third exam? I think you're trying to say like will be stuff covered since the third. I think it's like 2 of the 6 questions are on kinetics and electronic properties, and the other ones are cumulative. So maybe a third of the exam, a third to a half of it is the new stuff. The other stuff is all old stuff. Can we do more examples of Gibbs free energy examples? Yeah, we'll pull that up in a second. Let's do that. Let's hop over to free energy, and we'll do some examples of this. So Gibbs free energy, we learned about it with something like this. Let's walk through this example. It said an important way that you can manufacture silicon chips for semiconductors is through chemical vapor deposition, CVD, which happens at this high temperature, 1500 Kelvin, where in that reaction you have the following. You have silane, which is silicon chloride gas, reacting with hydrogen gas to form silicon, which is now a solid, and hydrogen chloride, so hydrochloric acid coming off as a gas. Pretty gnarly reaction, but you see that the product, they're all gaseous things, reactants and products, except for silicon. So technically this should allow you to grow silicon, nice pure silicon, if you can control the purity of your gases coming in. So it says, determine the value of the equilibrium constant. And what you are given is that the delta G naught for silane is negative 467 kilojoules per mole. And the delta G naught for hydrochloric gas is also given. So whenever you're doing free energy, it's always a couple things. First off, one equation that you have to know is this one. This equation right here is the main one. Delta G equals delta G naught plus RT natural log of K, where delta G naught is your change in the Gibbs free energy under standard state conditions. That means room temperature and one activity, right, for all your components. Then the second term is this RT natural log of K, right? Where that allows you to say, well, and it's usually RT natural log of Q, we say that K equals Q at equilibrium. That's a very specific scenario. When you are at equilibrium, then K equals Q. Where this accounts for non-ambient temperature, obviously, because we're giving R times T, but it also allows you to account for non-activity, non-unit activities for different things. So if you have lots more reactants or products, this is where that comes into effect, because we calculate Q as the ratio of our products to our reactants, right? In this case, in this class, we make the huge assumption that we're gonna ignore solids, and that all you really need to know is the ratio of the partial pressures of your products over your reactants. Where you raise the partial pressure, let's say of hydrochloric gas, right? In this one, because it's a product, I would say the partial pressure of HCl, but I would raise that to the fourth because it has a 4 exponent or 4 coefficient in front of it. That would be divided by the partial pressure of my hydrogen gas squared, multiplied by my partial pressure of my silane gas, SiCl4, to the 1 power. So if I knew what those partial pressures were, then I could calculate Q. In this case, it's asking us just to determine the equilibrium constant. So it's telling us like when these things reach an equilibrium, we can calculate what that ratio is, right? And that ratio is K. That K value we're going to be able to solve for. At equilibrium, the key value, whenever you say equilibrium, this guy over here, delta G is equal to 0, right? That's the whole point. If the change in energy is 0, that means that when you go from reactants to products, there's no net change, right? It's not that they want to go lower or higher, it's just equal. So that whole left-hand side of the equation goes to 0. So the right-hand side of the equation then becomes delta G naught, which we don't know, plus RT, we know that because we're given a temperature, times natural log of K. We're being asked to solve for K, so the only thing we need to know to finish this is we need to know what delta G naught is. Well, delta G naught's not too bad to figure out because that's just going to be products minus reactants, right? We know that there are 4 moles of our hydrochloric gas, and we know what the formation value of hydrochloric gas is individually. It's 103.8 kilojoules per mole. So since there's 4 moles, we do that. Silicon we don't include because it's in its elemental state at that temperature. So its formation energy to make silicon in its elemental state from silicon in its elemental state is no change in free energy. So it's 0, so I didn't write it down. Same thing on the reactant side. Hydrogen is in its elemental state, so we don't need to account for it. But silane gas we do need to account for, and we're given its value. So when we plug those in, now we can actually solve for K, and it's equal to some value. And that value, you could set that equal to these partial pressures, and let's say you knew 2 of them, you could solve for the third. I said if in the reactor the partial pressure of hydrogen was 0.8 and silane was 0.1, tell me now what's the amount of hydrochloric gas. Maybe you want to know that because you don't want a lot of hydrochloric gas coming out of your effluent. You could actually calculate, what is the partial pressure if you were to let this thing reach equilibrium. Okay. Would a good strategy for this test to be to go through the conceptual questions first and then the math questions? I think that's a great way to do it. Because this has more conceptual questions, those will be coming more from the textbook and the notes, which kind of like we've been doing today in this YouTube video would be a good start. But for the math ones, I would go back to former exam homework questions. For example, on homework 7 was on, what's this on? So this is like our deformation. So this is going to have like the Weibull question. I would make sure that you could go through like the Weibull solution. First off, before you even look at the solution, go back to the original question and be like, okay, how would I at least set this up? Don't redo it because you don't have time, but be like, what's the key equation? What's the order in which I do my steps? Make sure you could like jot those down. That should take 20 seconds. And then look through the solution and say, did they follow the same steps? And if not, what am I missing? Because I think a lot of problems that people come into is they'll know how to follow along with the solution, but that's different than being able to synthesize it yourself. This one says, deformation in ceramics versus metals and polymers. Will this be more conceptual or equation based? That will be conceptual. Like under the topic, like example, like viscoelastic creep. I would have put that on the study guide if that was something that's going to be showing up as an equation. We did a Gibbs example, the delta G example. Yeah, we did one of those. Or delta G star, maybe that's from kinetics. Delta G star example would just be calculating delta G star. We're giving you some equations here. For example, if you knew those values, it's as simple as plugging those in. Or if it's been undercooled, right? Now you can modify that to account for undercooling. So there's some of those done in this homework. So that's the last homework, the solutions of which should be posted. If you look on the book problems, there's a few where we did that. So yeah, right here, for example, 11.3a, if you look in the solutions, it walks you through how to actually do the math on that. You can double check that you're getting the same things. On those, watch the units. Watch to make sure that the units cancel out. Like if we're talking about like a nano-sized particle, that might be in nanometers. Oh, dog. But here it's in joules per meter squared. So make sure that your meters have to cancel with meters. things like that, I think is where oftentimes see things go wrong there. How about this? It says, will the final be graded the same day, similar to other midterms? Yeah, we plan on grading it the exact same day. I do have a dinner I have to go to for a faculty thing, which will set us back a little bit. And it's also 6 problems instead of 3. So I hope we can finish it that night, but that is our effort. That is always our goal, to finish that night. And in 10 years, we've only had to grade it not the same day, like once or twice, which is pretty rad. Can we do one for the R cation to R anion problem? That's not on the study guide, so let's skip that. And then, did you get the notes? I assume that's taken care of. Okay, we got 10 minutes left. Are there other questions that y'all want to ask? Do people ever finish the exam early? For sure. The final exam is regularly has a significant chunk of the class finishing early. Oh yeah. Yeah, if you're just joining this because you're some subscriber on YouTube, thanks for being here. That's awesome. But this is specifically for the final exam this semester. So even though we cover R cation to R anion ratio in the course, we're not covering it in this study session. Good question, though. Are we allowed to use the final notes sheet that was posted? The final notes sheet that was posted, I don't know what that is. Maybe that's something you guys have. If you're going to bring something in, it has to be handwritten for your notes. You can handwrite it into an iPad, right? Like I do with my screen, and then print that, I guess, if you want, but not typed up, or not like posted solutions from homeworks and stuff. Just some random personal studying for MEMS final. Good luck, random person, on your MEMS final tomorrow. Okay, anything else? We got 10 minutes left. People got other questions that I can answer? I'll pull up the study guide one more time right here. This is the exam, pretty much in the same order. Anything still feel scary? You get note sheet, 4 note sheets. You can do front and back. Use it at your own peril. If you fill it up with tiny little font, you might spend your whole time trying to flip through it, trying to find the example, just the one that you're thinking of. And it might, just like usual, you have to work fairly quickly. So I would prioritize having all the content there, but easily found, than, having to pull out a microscope to find it or something. Greetings from UC Merced. Hey, UC Merced. I would love to come out there someday. Maybe I will. I was just at UC Irvine last week giving a talk. Any other questions? Best pre-exam night practices. I would legit look through like this exam study guide. If you see crack growth, flaw size growth over fatigue loading, and that scares you, I would go back to the homework and again look at the homework question, not the solution yet, and just write down the steps to answering the question that was provided. Once you've written down the steps, which again, you can do that in 10 or 20 seconds, then I would go back over and make sure that the solution matches those same steps. Because you don't have time to go back and redo all the homework. And that took hours and hours. But you can go through the steps and make sure that you can follow the steps. And remember in this class, like if you look back at all the previous exams, every one of them, look how like heavily we weight partial credit. Like for this one here, it said like, this one is about the glass transition of this material can be calculated from this equation where this and this is that. Calculate, for a sample that has this degree of polymerization, what type of fracture would you expect? So of the 10 points on this, 3 of them come from first calculating the MER weight. 3 of them come from turning that into a molecular weight. 2 points come from solving for the TG for that material by plugging into this equation. And then 2 points come from the actual ductile to brittle assessment. So if all you do is come and you say like ductile, then I can't give you any of these 8 points, right? I can just say 2 points. And I don't know if you just took a guess or what. And on the other hand, if you're doing the math and you mess up something about this molecular weight, like you made a math error, well, a math error on something worth 3 points, I'll still give you like 2 out of the 3 points if you just made like a silly math error probably. And you can still get 7 out of 8 points if you follow these same steps. So showing your work and showing your work clearly and breaking it into steps is definitely the way to go to maximize partial credit. We give as much partial credit as we can. Let's see. Can you walk through the Avrami? That was the very, I think, first one we did. So this video will be posted to my YouTube page on the Intro to MSE playlist. So if you look through my channel on YouTube, there's a playlist for Intro to MSE or Material Science 101. If you scroll to the very bottom, it'll be the last video in that series, and that should be up tonight. As soon as this is over, I think it'll go straight there. So you'll see the Avrami equation was the first thing we covered. Did we go over dopants? We did. You can also find that. Would I rather fight a shark or a lion? 100%. Sharks and water scare the crap out of me. You're just like, humans don't belong in the ocean. Sharks would straight up eat us. A lion would still beat me, but like, I would like fool myself into thinking I have a chance. A shark, you're just gone. Under electronic properties, what do you mean by know how basic devices work? I just am nervous. I'll miss something. So if you go back to chapter 12, the latter third of this chapter, before dielectrics actually. So the middle third, roughly, right here, we start talking about basic devices. Right here, this section where it says PN junction as the basis of critical semiconductor devices. I'll just go through this, right? Like, what is a rectifying junction? It takes an AC signal and turns it into a DC signal by chopping out the signal for either the positive or the negative part. So it does that by basically saying when the electrons travel away from this junction, the holes in electrons travel away from it, you get just regular current. But when they travel into that junction, you get recombination. Like, that's an example of understanding how like a PN junction works to form a rectifying junction. Same thing for solar panels, right? You could describe how solar panels work. We talked about that earlier in the notes. Like, in comes light in this region, right? In comes a photon here, right? It hits an electron here, putting the electron up here and the hole down here, right? So then they can separate and you can get current collection from a photovoltaic, right? Same thing with transistors. We talked about those. Specifically, I called out a MOSFET, so I would make sure, darn sure, that you know how these things work, MOSFETs. We've got it all sort of explained here in text, but we also talked about it in this video earlier. Avrami equations at the beginning, yep. I think, yeah, yep. We talked about the MOSFETs earlier in the video. Even if we miscalculate one of the parts of an equation and we proceed to finish with the wrong numbers, we still get a word. Yeah, absolutely. So let's say if we go back to some exam question, right? This one, for example. This one was exam 2, and you were supposed to do, whatever. Like, let's say like the very first step was determining the lattice parameter, and you didn't get it. Maybe you don't even know how to do it. You're like, oh, dang, I didn't even... my brain wasn't even working to realize that it's this combination of radii that gives you the lattice parameters. If you just said like, I can't remember how to figure out the lattice parameter, let's assume that it equals 1 angstrom, right? Which is like a silly thing because it's not that value. But then you do all the rest of the steps correctly, you would get, in this case, 12 out of 15 points. Even though the first part was totally nonsense, if you propagate that forward, we don't continue penalizing you for an error made one time, which is why it breaks my heart when I see people like, I don't know how to do this. I don't know how to get started on this problem. It's like, okay, so make an assumption that gets you halfway through it and then finish it the rest of the way. You'll get most of your points. Yeah, and then what was the lowest score in the last year's final? I don't remember. I don't recall that number. Finals are typically a little bit better than the midterms. I don't have to curve them as much. Yeah. Okay. 4 minutes left. Any last questions I can help y'all with? Will we be able to assume that nucleation is a sphere? Not necessarily, Mary. I might ask you to calculate it based off of a cube, for example. Like, how would the math change if it was for a cube? And if you want to remember how to do that for a couple different shapes, this was one of the examples on, I think, homework 10. I think the book problem has you do a few of these. Yeah, here it is, comparing a cube and a sphere. We actually do the math on that first one. Yeah, maybe that might have been a test question from years past that I had you do, but I think I took it off. But part of it is here on that very first one from chapter 11. But yeah, that would be fair game to ask something like that. Okay, 3 minutes left. Other questions? When will final grades for the whole class be submitted? Yeah, good question. As soon as the TAs finish grading all the homeworks, then I will calculate. I will run it through my Python script, Gradetron 5000, which takes all the, for this class. Remember, for these classes, if I go to material science students for a minute. I look at the syllabus. They get graded slightly different than the mechanical engineers because they have a lab that I have to incorporate. So for material scientists, this is their breakdown. Their total homework points are only worth 15% of their grade. Midterms are worth 30, finals worth 25, labs are worth 20, and then the reading quizzes and labs are worth 5. So it's slightly different than the mechanical engineers, which is 30, 30, 30, 10. It skips because you don't have a lab component. But I run that through as quick as I have all the data to run it through. So if you tell the TAs pretty please, as soon as you're done with finals, we would love to have the homeworks graded as soon as they finish grading the homeworks, and we will have the final graded tomorrow night. Then technically we can post the scores probably by this weekend. I would guess we'd be able to have them done. I do not take bribes, and there will be a curve, but I can't guarantee what the curve will be. Any other questions? 1 minute left. Any burning questions about material science? You have your last review with somebody who can tell you about it. Most productive review that. Okay, glad it was helpful. All right, everybody. Get some sleep tonight. Don't stay up crazy late. I think it would be better to get a good night's rest and a big breakfast and come in ready to roll. But best of luck to you all studying. I will end this review now, and I will go ahead and post it to YouTube. So if you wanted to go back and find something, you can. Oh, somebody's asking about the bubble zone one more time. Basically, if you look at this grade, I'll go back to the syllabus right here. So you see that in this approximate grading scale, there are these regions between the block grades. So if you get above a 92%, you will get an A. But if you get between 92 and 87, that would either be an A- or a B+, and I will either roll you up or roll you down based off of whether you showed improvement over the course, whether you were present in class most of the time, whether you turned in your homeworks. If there's a bunch of missing scores on homeworks, I'm going to roll you down. If your grades got progressively worse, I'm probably going to roll you down. If you go the other way, I will roll you up. Okay, thank you all so much, and I will see you tomorrow for, get ready for it, Roman Empire themed final exam. It's going to be fantastic. We'll see you guys tomorrow in class.